Okay, today we will begin with an example of Fulkerson's method on a very small network. Suppose the given network has 4 nodes, the source and the sink node and the 2 additional nodes. What you see here are the capacities of the various edges. So the step 1 initializes the flow to 0 value. So we have values 0 out of given capacity on each of the edges. Hence, the residual graph is precisely the initial network. So let us say the residual graph G naught is we have this. Now in this graph, okay, my mistake, we have decided to put the direction as this. So in this we have to choose a directed path from source to the sink, and suppose we choose the path to be this. So that would be S, say this is x and y and t. So I choose my path to be S, x, y, t, path P naught. The minimum capacity on this path is 5, hence we can augment 5 units of flow on this. So in the next graph, the flow is, so maybe I can show the flow here, will be 5 units here, this will be 5 and this will be 5. So the edges of the residual graph, I will still have an edge with 5 units this way, but I will have a reverse edge also 5. We will have a edge with 10 capacity this way. Now this is saturated, so this edge will go away and we will have edge with 5 capacity, but we also had additional 7 capacity. So this will be a 12 capacity edge. This is 15 and this has 3 and the reverse edge has 5 capacity. So we have the new graph. Now suppose we choose a path to be S, Y, X. So let us choose path P1 to be S, Y, X, T. On this path we have 10, 12 and 15, hence 10 is the minimum capacity, so I can augment 10 units. So this flow will be 10, we will augment 10, so this will be 0 and this will be 7. A total net movement is 5, will be 5 here, and this will be 10 units. The new residual graph will have still a 5 capacity edge this way and a 5 capacity edge this way. This time there is a 10 capacity because this is saturated this way. Now we have a total capacity this way is 10 units and 2 units this way. So this is 10 and this is 2. Capacity of 5 this way and 10 this way. And we have a capacity of 3 and a capacity of 5 in the reverse direction. Now we have one possible directed edge is S, X, T. So suppose we choose the next path to be S, X, T. There are two edges, both have capacity 5. So the minimum capacity is 5. We can augment 5 units of flow in this. So that gives me 10 units here and 15 units this way. And the residual graph for this flow we have a saturated edge from here to here. So there is a reverse edge of 10 capacity and this is also saturated. So we have a reverse edge of 15. The other edges are untouched. We will have a 10 this way and 2 this way. I will have a 10 capacity edge this way, a 5 this way and a 3 this way. In this case, since right here we see there is no way to get out of S, there cannot be a path from S to T. So this is the end of the algorithm. We have reached a stage where there is no path, hence this flow has to be the maximum flow. And notice that the total fluid exiting from S is 10 plus 10 units. So the mod, so maximum flow is 20 units. Now in this example what we notice is that there was an edge xy which was once saturated and hence we had no edge going from x to y. At a later stage what we notice is that x to y edge re-emerges at some stage. Hence it is possible that a certain edge which vanishes at some stage in the residual graph may reappear. So in general there is no way to tell whether these iterations will terminate, and this is the problem with this general method. Unless we give a way to guarantee the termination of these iterations, this cannot be considered as an algorithm in classical sense. Now we want to make one observation in this context. Our notations, first of all, we will denote the successive residual graphs by G0, G1, G2, G3. the path computed, the respective paths computed are P0, P1, P2, etc. And one more notation I will use dl x to denote distance from S to vertex x in graph GL. These are the three notations I need from now onwards. So, we want to make an observation that suppose edge UV is not present in GL, but is present in GL plus 1. Suppose it so happens that there was an edge which is not available in GL, but is present in GL plus 1. For example, edge xy is not present in this graph, but it is present in the next one. Then what can we say about this particular edge? Why is this not present here? The reason must be that that is a saturated edge. There is no capacity there. Something must have happened in our augmentation such that the capacity from x to y re-emerges, and that can happen only if we augment flow in such a way that there is new flow from y to x. And you notice that there is edge yx present in the path P1. So, we are saying that if UV is not present in GL but present in GL plus 1, then edge VU must be present in PL, the path computed from GL. Now, we would like to prove an interesting and a significant result which leads to a very interesting way to modify this method into an effective algorithm. So, we have a lemma which says for all vertices x dl of x is less than equal to dl plus 1 of x. The distance from S to x in GL cannot be more than distance from S to x in the next graph. Let us try to prove this. We will prove this result by induction. What we will do is that we will take this measure for induction, the distances of vertices from S in GL plus 1. So, now base case, notice that the only vertex which has distance 0 from S is S, and that is true in every single graph. Hence, what we do know is that for V equal to S, dl of S is 0, which is also in the next graph. So this inequality holds for the vertex which has dl plus 1 value 0. There is no other vertex with distance 0, hence we have proven this claim for the distance 0 case. Now we take the induction step. And from induction hypothesis, suppose the claim is true, the claim holds for all vertices V such that dl plus 1 of V is less than k. So if we notice that there is a vertex with a dl plus 1V less than or equal to k minus 1, the claim holds. And we want to prove that the same holds when this distance is equal to k for all those vertices. So now suppose let U be a vertex such that dl plus 1 of U is equal to k. Distance is the length of the shortest path. So there exists a path S x1 x2 xk minus 1 U, which is shortest, in GL plus 1. That is because we are given so. Now, as a result, what we notice is that the vertex xk minus 1 has a distance k minus 1. So dl plus 1 of x k minus 1 is k minus 1. But this qualifies under this condition. Hence, from induction hypothesis, dl of x k minus 1 is less than equal to dl plus 1 of x k minus 1, which is equal to k minus 1. So in graph GL also, the distance of x k minus 1 from S is less than equal to k minus 1. Now let's say we have a path, suppose in GL we have a path S y1 y2 y j minus 2 x k minus 1. We have a shortest path, assume it is shortest. And it is not suppose, we do have. So in GL we have a path where j has to be less than equal to k, because the length of this path is j minus 1 and that should be less than equal to k minus 1. Now let us take a look at this edge k minus 1 u. Now this edge is present in GL plus 1. So there are two possibilities, either it is present in GL or it is not. So we will consider two cases. Case 1, the edge xk minus 1u is present in GL, and case 2 is not present. Now consider the first case. If indeed this edge is available to us, then I can take this path and append this edge to it. That will give me a walk of length k. So there has to be a path of length less than or equal to k from S to U, and that is what we want to show, that if dl plus 1u is equal to k, then there is a path of length no more than k from S to U in dl as well. Okay, so we have first case where xk minus 1u is in GL also. So we have a walk S y1 y2 y j minus 2 xk minus 1 u in GL. This is a walk from S to U, hence there is a, and the length of this walk is k, sorry, it is j, the length of this is j, of length j, which is less than equal to k, as we have seen earlier. Now if the walk is of length limited by k, then there has to be a path inside this which also is not greater than k. Hence the shortest path length from S to U in GL, dLu has to be less than equal to k. Now let us take a look at the case 2. In this case, the edge xk minus 1 u was not present in GL, but certainly was available in GL plus 1. From our observation, we know that edge u comma xk minus 1 must be present in PL. In the augmentation path computed from GL must have had this edge. Okay. Now, so and notice that the augmentation path, if we take this to be the shortest path, then dl of u is dl x k minus 1 minus 1. So now I am assuming that my augmentation path is a shortest path from S to T. Under that assumption, we have this available. And from induction hypothesis, this is less than equal to dl plus 1 xk minus 1 minus 1 and that in turn is less than equal to k minus 1 minus 1 is k minus 2. So, if I assume that my PL is the shortest path, then once again, okay, this is of course less than equal to dl plus 1 u minus 2. So, in both the cases we have, okay, this is actually equal to dl plus 1 u. So, either way we have shown that dl of u is less than equal to dl plus 1 u if the augmentation path is the shortest path. So, the lemma, to be precise, is this is true if each pi is a shortest path. Now, we will propose a modification or actually an addendum in the Ford-Fulkerson algorithm, and which is proposed by originally Edmond and Karp. So, it is known as an Edmond Karp algorithm. This algorithm is nothing but Ford-Fulkerson algorithm, but they say in addition to this, each augmentation path must be chosen as a shortest path. From S to T. This is the only modification in the method. And now we are ready to show that the number of iterations are going to be bounded. So, let us try to prove, actually let us try to determine the number of iterations will be at most how much, and from that we will be able to determine the complexity of the algorithm. So, now the next thing I would like to prove is a simple corollary. That is, in Edmond Karp algorithm, dl prime of x is less than equal to dl double prime of x for all x and for all L prime less than L double prime. That is, in any subsequent iteration, the distance of a vertex can never decrease. Now, that is a trivial consequence of this lemma, because if the distance in L plus 1 is greater than or equal to distance in L, then iteratively the distance in L plus 2 will be greater than or equal to distance in L plus 1 and so on. So, this is trivially true. Okay. Now, we are going to show the change in distance in a special situation is little bit greater than a simple inequality. So, we have a lemma that suppose some edge uv is one of the saturated edges in PL. What I mean is that in the graph GL, the path that we had selected was PL, and the flow that was computed was looking at the minimum capacity, and the minimum among the edges which had minimum capacity was this one. So now on this edge we have fullest possible flow, hence this edge was saturated in this path. Now it is clear therefore that this edge will be absent in the subsequent graph, namely G L plus 1. But suppose suppose UV is present in the augmentation path PL prime for some L prime greater than L. We know, of course, this cannot happen for L prime equal to L plus 1, but maybe some later stage, as we had seen in our example, it had reappeared. So it so happens that the same edge is present in the augmentation path of a later graph. Then in this case we can say that d L prime of u is greater than equal to d L of u plus 2. So we already know, of course, this claim we know from our previous result. Now this is a stronger claim for such special cases. So how do we prove this? Now notice that this edge was saturated, there was no further capacity left for appending any flow in this direction. If it again shows up in L prime, that means somewhere in between there must be some graph GL double prime where we must have sent a flow through edge VU. If you append a flow in the direction VU, then this flow will create some residual capacity for edge UV. It will reappear in the subsequent stage. So there exists L double prime where L double prime is between L and L prime such that edge VU appears in PL double prime. I hope that is clear, because here we had made a flow from V to U, thereby we have created capacity from U to V, and hence in L double prime plus 1 stage the edge UV reappears. Okay. So now let us see what are the facts we know. We know that UV was present in PL and V was present in PL double prime. So some facts here. Namely dl of u plus 1 is d L double prime, sorry, dl of V. My mistake, right. So we have dl because in PL edge UV occurs, U occurs first, V occurs later. This is the shortest path. So the distance from S to U has to be 1 less than the distance from S to V. The reverse occurs in PL double prime. So we have dl double prime V plus 1 is dl double prime of U. We have this as well. From our corollary, we have a few additional facts. We know that dl of U is less than equal to dl double prime of U, which is less than equal to dl prime of U. And finally, we also have dl of V is dl double prime of V, which is less than equal to dl prime of V. We have these 4 facts with us. What do we want to prove? We want to show this inequality. So let us say we look at the value of dl U plus 2. dl U plus 1 is dl V. So this is equal to dl V plus 1. This is less than equal to dl double prime of V plus 1, because this is greater than equal to this. dl double prime V plus 1 is equal to dl double prime U. This is equal to dl double prime U. dl double prime U is less than equal to dl prime. So this is dl prime of U. This is all we needed to prove. This is the claim. So what we notice is that if the same edge reappears on a subsequent augmentation path, and in the first occurrence it was a saturation edge, then the distance of vertex U increases in the second occurrence by at least 2. So now I am claiming a corollary to this claim is that no edge can occur more than n by 2 times. That is, in n by 2 iterations, distinct iterations, no edge can occur as a saturation edge. So suppose, let us try to prove this. Suppose edge UV occurs as a saturated edge in the iteration number L0, L1, L2, LP. So these are the different successive, and I am assuming that it first occurred in iteration L0, then in L1, then in L2 and so on. So, we know that dLp of u has to be greater than equal to d of Lp minus 1 of u plus 2. And in dLp minus 2 u plus 4. So, finally, in dL1 the inequality is that this is at least 2p smaller than this dL0. Sorry. So, what we notice is the shortest distance in GLP has to be at least 2p, maybe at least 2p plus 1 if it is not s, but at least 2p. But the distance can never be more than n minus 1 in a graph of n vertices. So, since distances are always less than equal to n minus 1, we conclude that p has to be less than or equal to n minus 1 over 2. What this result does is that it puts a bound on number of times a particular edge can occur as a saturated edge in different iterations, in different augmentation path. Now, this is all we need. We have only so many edges. We have n square edges. In every pass, in every residual graph, the augmentation path that we compute must have at least one saturated edge, and each edge is allowed to appear at most n by 2 times. That allows me to put a bound on the total number of iterations. So, let us do the last step. Okay. So, we have a simple result now, theorem. Let the number of edges with positive capacity in the network be n. Then the number of iterations in Edmond Karp algorithm will be at most n times n. If there are m edges in a network, then at most 2m edges can occur, because if you have an edge xy to begin with, but you have 0 capacity here, but in some subsequent graphs you may very well have an edge yx in the residual graphs. So, the total number of distinct edges that can show up in various residual graphs can be at most 2m. So, there are at most 2m edges in all GIs. These are the only edges that can show up. Each edge can be a saturation edge in at most n by 2 iterations. Every iteration must have at least one saturation edge. So, we can directly say that number of iteration can never exceed this number. If you have more than this many iterations, then at least one edge must have occurred n by 2 plus 1 times, but that is not allowed. So, once we have put a bound on this, the total time complexity can be determined now. In each iteration, we compute a shortest path from S to T, and then only on those edges we need to modify the capacities. Hence, only those edges will get modified in the next residual graph. So, and that modification takes only order n time, because on a path there are only at most n edges. So, the time to compute a shortest path and time to update the graph is only order m plus n, and there are at most mn iterations. So, the time complexity of Edmond Karp's algorithm is m plus n times mn. So, that completes our discussion of the flow networks. So, from next lecture we will begin the discussion of matrix operations, and in particular we will discuss matrix multiplication, inversion and decomposition.